I have the pleasure of introducing Fabian and Marius, who will be presenting on the mysterious life of an exception. So please welcome Fabian and Marius.
Thank you.
Yeah, thank you. And hi all, I hope you had a beautiful lunch. Hi. My name is Marius.
I'm Fabian.
And we looked into exception handling a lot lately, like really, really a lot. And we would like to share a little bit of what we found. Or more specific, we want to basically convey all the complex internal mechanisms going on from a normal exceptions.
So, to tell you a little bit about what we're going to see, we'll talk a lot about how exceptions are implemented by compilers, by compiled languages. We'll look at how to reverse engineer exceptions from a binary. So our talk will be very focused on reverse engineering, not as much on exploitation. We won't be going into any bugs or anything that is exploitation related, so purely reverse engineering. We'll be talking about exceptions and kind of low-level exceptions, but not these kinds of exceptions that your compiler and that your processor emits when it's trapping, for example, on a floating point exception. For example, these ones on the ARM reference manual. We won't be talking about those.
We are also not going to talk about exceptions in scripting language like Python as we see here, right? Like a try, catch, finally block. No, that's not what we're interested in. What we are interested in are exceptions in compiled languages. Specifically, we are trying to aim shed some light on C++ exception, and here's just the most basic example we could come up with to show how it looks like, right? We have a try block with throw some runtime error and a catch-all handler just below, which, basically catches it. So what happens internally?
The first thing that's important to note is that exceptions can be thrown across function boundaries. For example, here we have a function foo that throws an exception that's being called by a function bar. Bar has a try block and a catch handler, and when the exception is thrown in foo, code that happens after that throw doesn't get executed. Instead, we will go directly to the exception block, skipping any of that code. There's an exception to this exception though. When we have any cleanup related code, like for example destructors being called, memory things being cleaned up on the way, those will get called when going from a throw statement to the catch statement. So that's kind of an interesting side effect that we see here.
Another interesting thing to note about the exceptions we are talking about is that they are typed. Like here, we see a bar function which throws a foo exception, but it registers two catch handlers, one for a foo exception and one for a bar exception. So basically, when we throw the foo exception now, we definitely would end up where we expected in the catch exception handler for foo. So now we saw like just a little bit already about the C++ language semantics, but this is high-level stuff, right? We want to do the low-level things. So what happens under the hood? We will talk a little bit now about unwinding to see how we actually get to the right places during exception handling. This leads us on a small side quest on the DWARF debugging format. From there, we will continue and be talking about the personality routine, which is one of the, let's say, core points during exception handling. This will be invoked a lot, and we will discuss it quite in depth. From there, we will go and describe the language-specific data areas. And lastly, we will actually arrive at the actual catch handler, which we just saw, which in terminology are landing pads. And we will also look into cleanup handlers. So that's the roadmap here, what's now going to happen. So all of you, let's unwind.
So when a function is called, it has a stack frame. The stack frame is usually between a frame pointer and a stack pointer. When that function calls another function, in this case bar, another stack frame is allocated underneath this initial frame. We move the frame pointer and the stack pointer accordingly, save the instruction pointer pointing to where execution would resume after returning. And the frame pointer is also saved on the stack, the original one. If that function then again calls another function, again we allocate a new stack frame, adjust the frame pointer and stack pointer, save the instruction pointer after where we would return, save the frame pointer. But now the interesting part is, what if we don't return? What if we instead throw an exception? Then we'll have to go back up the stack to figure out where to continue.
And that's the job of the unwinder.
Exactly. So this is pretty simple. If we have a frame pointer, we set the stack pointer to the frame pointer, pop the frame pointer off the stack, and then we can go up the stack. And that way we can find all of the saved instruction pointers on the way.
But you just told us it's very simple if we have a frame pointer, right? But nowadays, binary often omits the frame pointer. Like a lot of things out there are compiled with f-omit frame pointer for additional performance gains. So how do we unwind in this specific case?
Exactly. So frames in that case often have a fixed size. For example, here we have a frame of size 0x20. We just subtract that from the stack pointer and just adjust the stack pointer using a constant size. Then the next frame might have a size of 0x30, and then we subtract that again, and that's how we find all of the saved instruction pointers on the way.
These are still like just static variables or static values, right? Like what if we have dynamic memory on the stack? Like for instance with our all-ferret function alloc A, which dynamically allocates a chunk of memory on the stack.
Then things become more complicated. We might have to calculate on the fly how big the stack frame is. For example, here we have an array of size n, and then we will have to add a constant onto that to account for all of the static variables on the stack. So as you see, there's lots of different cases that we can run into while unwinding, and we need to somehow store that metadata somewhere. So for every function, we need to store how to restore the stack pointer, whether it's through a frame pointer, whether we have a constant frame size, how to calculate the frame size if it's more complicated, and if it uses any registers, we need to know how to restore those to calculate all of these things from there.
And that's where our small side quest to the DWARF debugging format starts.
So let's talk about DWARF. ELF binaries have a section called frame in them. Within there, we have two different data structures, which we'll go into in brief detail. There are frame description entries for each frame, and as the name states, they describe the layout of each frame. Each of those frame description entries has a range of program counters or addresses it corresponds to. So it has the start address for which it is valid, and a range after that. Furthermore, it has a pointer to a common information entry, which is there's a many-to-one relationship between frame description entries. Multiple frame description entries can share a single common information entry. There are DWARF instructions in the common information entries. These are a common prologue to all of the other DWARF instructions that are later on in the frame description entries. So we will first go through all of the instructions in the common information entry and then into the more specific ones for each function. So how do we locate these? There's another section called the frame header, which has a table corresponding to each function start and frame description offset. And all of these point to the frame description entries. And through there, we can, again, find the common information entries. So what can we use these for? If we're reverse engineering, the information where functions start and their stack layout, it might be very interesting to us. So we can use the frame description entries for finding functions and their stack layouts, and the common information entries to figure out what compilation units were used for each function. So we can group functions that way. We can figure out what kind of modularization was in the binary and maybe infer some information about the structure of the code we're looking at.
And the cool stuff about this is that it's not only, I mean, you may think, oh, DWARF debugging information, binaries need to be compiled with debugging information. No, that's not the case here. As we're doing exception handling, these things need to be there. So we find them even in strip binaries.
Exactly. So let's look at one example of a DWARF debug information. This is all of the DWARF, this is output from a program called DWARF dump. And it's what's happening here? This is output from a DWARF dump. And here we can see the different operations that are being run for a specific frame description entry. At the bottom, you can see that there are different ranges of addresses which have different unwinding instructions according to them. So for example, the DWCFA advanced location opcode will define which range of addresses we're looking at, and the other ones show, for example, which registers are located where on the stack.
We can't, unfortunately, go into all the detail here of DWARF because, or especially DWARF bytecode, this would kind of like go out of the scope of this talk. So let's just quickly summarize what we saw and recap what DWARF is for. It's a bytecoded debugging format which allows us to calculate stack frames and register values. And for the purpose of unwinding, it's really invaluable. It needs to be there. Another nice thing here is that from all what we saw by now already, we can basically create backtraces. So when GDB or whatever ferret debugger you have needs to backtrace after you set a breakpoint or hit a AAA instruction counter, GDB will go through the very same kind of structures we just explained. But this is just one part, right? We wanted to talk about exception handling. So how do we do this? For that, we need to locate the handlers, so the specific exception handlers, and we need to find them.
So let's go back to the example of the stack that we looked at earlier, and this time we have a try and a catch handler in the bottommost function. So when we're unwinding, we'll first look at the saved instruction pointer here and check, does it point into a try block? It doesn't, so we continue unwinding. Then we do the same thing again, but this time our saved instruction pointer points into the range of a try block. So now we need to do something differently, and there's a function that checks this on the way, and that we'll go into more detail about that now.
Exactly. This function is a personality routine. And there's not just the one personality routine, but a bunch of them. Here we see GCC personality, which is for C programs. But there's also GNAT personality for ADA programs, GCC Go for Go, GNU Objective-C for Objective-C, you name it, right? Like all those compiled languages which do exception handling do need a personality routine. And in this talk, we are focusing on GXX personality, which is the one for C++, as we saw the code snippets earlier on. Another small thing about the personality routine is the part on the right. So this is basically encoding which style or which flavor of exception handling is done here. SJ0 means setjump-based exception handling. IMP stands for imperative, which is used by
Windows structured exceptions.
Thank you so much. And then what we are looking at is V0, which is the plain old DWARF-based exception handling. All right, what does this personality routine do? We thought it's very good to start looking at it on an API level because it already gives a good insight about all the different steps which needs to be done during exception handling, when unwinding, when calling the personality routine. But first things first, we are looking here once again into C++. So we cannot use just the standard personality routine. We use the GXX personality routine. Also, we will show a couple of code samples and structure definitions. These are all taken from libgcc. There are also other implementations for this. Okay, let's start. The personality routine, of course, needs to return something, right? It returns an unwind reason code, which is basically just one of the following values in these little enum. There are a couple of things to observe here. Firstly, what we already see, there's something about phase 1, phase 2. So there must be multiple phases involved. Then we see something which says handler found, like URC handler found. So the personality routine can return, hey, we found a handler. Then there's also something which is called install context, which the personality routine uses to basically signalize to the unwinder that the context is all prepared to transfer execution to the actual catch handler, to the landing pad. And lastly, another thing to note is the last entry of this enum, which is continue unwind, which is basically just a no, nothing to see here. I went through this frame with this personality routine. I could not find any handler, so let's move on. Okay, the arguments of the personality routine. The first one is kind of boring, I would say. It's version, which is always 1 for what we are looking at here. So let's skip that and look at the second, which are the actions. Actions drive what the personality routine will do. And we see here, again, multiple actions, which are clearly defined, and these are just a bit mask. We again see the notion of multiple phases, this time a cleanup phase and a search phase. Then we do see that there is a handler frame, which basically means or tells to the unwind routine, okay, now you're going to do whatever you need to do on the actual frame, which has a handler. And yeah, let's continue to the exception class, which is basically, if we would start C++ compiled binary and on G++, we would find this if we break in the personality routine in the exception class. So this is just a small byte string, which is constant in our case. And basically, it's nothing to be scared about. So maybe some of you already tried to decoding what it means. It's basically split in 2 parts, the upper half and the lower half. The upper half decodes the vendor, the lower half the language, which eventually, in our case, will be just the ASCII representation of GNU-C for vendor and C++ for language. So really just telling the unwinder what kind of exception we are handling right now. The reason that we need this is basically multi-language interactions. There's a possibility for throwing an exception in Java and want to handle it in C++, then this kind of exception class needs to be checked. Let's talk about the next argument, the exception object. So the exception object's first part in the struct is exactly what we just saw, the exception class. So this is literally a one-to-one copy, just that this time it's also in the object. Then the second parameter, or the second part of the struct, is a function pointer to an exception cleanup function. This function will be called after the exception was handled and executed. So assuming a handler was found, after execution, control goes over there to clean up whatever the catch handler or the exception did on the stack. Lastly, we have two private words. These are meant to be used by the unwinder and not by the personality routine. So the idea is basically that the unwinder can keep some state between multiple invocations of the personality routine. For instance, it will, when a handler is found, decode the fact inside the private to word. Lastly, in the personality routine, we have the context. This context is really highly specific to the unwinding implementation and to the system and instruction set architecture we are running to. In the case of C++, libgcc as we're looking at, and especially in the unwind DWARF 2 implementation, the unwind context looks something like that. These are just the first couple of parts of the structure. There's way more, but this is the start, and we already have a couple of interesting parts in here. So first, we have the register context. So these are the register as restored by DWARF during the unwinding process to continue the unwinding and so on and so forth. We have a pointer to the CFA, so that is the call frame address, which basically encodes which frame or which stack frame we are currently operating on during unwinding. Similar, we have the return address, which also comes from the call frame eventually, but it really helps us to in the unwinding, easily continue unwinding once we are done, or once we need to continue unwinding. And then the most button part is the LSDA, the language-specific data area, which is really the core part which helps the unwind or helps the personality routine to figure out if the exception object we're currently encountering can be handled by the routine or by the frame we are just looking at.
Yeah, so as reverse engineers, this is really the meat of what we want to look at. It encodes what exceptions we're handling, where the handlers are, and so on. So let's look at a function that has a corresponding LSDA in its frame description entry, and on the left we have a try block and a catch block. Inside the LSDA, we have a call site table. This call site table contains entries which have a pointer to the start or an offset to the start of each try block and how long that try block is. Furthermore, they have an offset to where the landing pad is for this try block. And finally, they also contain an action index which points into an actions list. Inside this actions list, we have a set of entries containing a filter value which points into a types table. These can be chained so that you can have multiple types corresponding to a specific call site entry. So like in here, we now have multiple types that we can encode for a specific try and catch block. This types table, inside the header of the LSDA, we have an offset into the types table. From this offset, positive filter values are subtracted, and these correspond to catch handlers, and negative ones correspond to cleanup handlers. In the types table, we have pointers to the runtime type information inside the binary, so we can figure out what the actual types are. This is language specific, but all of the languages we looked at use the same layout. So the runtime type information might be different, but in general, this seems to be the common layout for all of the languages. All right. So how do we find these language-specific data areas? Inside the common information entries, there are, and in the frame description entries, which we talked about earlier, there are two fields described by a string, which is called the augmentation string. This augmentation string contains a single letter for each field that is present or not present in the corresponding augmentation data areas. For example, the letter Z says there is a length field in both the common information entry and the frame description entry, and this length says how long this field is. The letter P says there is a personality routine inside the common information entry. That makes sense because, you know, per compilation unit, you would probably not be mixing different languages. This is an encoded pointer using an encoding and an offset, and both of these are stored inside the common information entry. We'll get into encodings in a second. Thirdly, the letter L in the augmentation string indicates that there is a language-specific data area for which the encoding is stored in the common information area, and the pointer is stored in the frame description area. That makes sense because every function has its own LSDA. And finally, R just says there might be a non-standard encoding for the program counters, ranges, and so on. So this way we can figure out where those language-specific data areas are, and from there we can reverse engineer all of the exception information. So encodings are the other interesting thing. These are defined in the DWARF standard. Encodings are indicated using a single byte where the low nibble says what type is being used for the pointer. For example, 4 stands for an unsigned 64-bit integer, but there are 2 more types to look at. These are little endian base 128 numbers. These are variable width numbers, where the top bit of each byte says whether this to continue including more bytes into the number. So that's somewhat like UTF-8. The top nibble of the encoding specifies whether this is an absolute pointer or an offset, and to what this offset is relative. For example, whether it's relative to the current program counter or to the EH frame header. So when you're decoding these, you will be encountering these encodings, and you'll need to check what encoding to look at pointers in. There's a specific encoding for omitted pointers. If something is missing, that'll be indicated by an OXFF. So you'll see that a lot when things are missing from the LSDA. Their corresponding encodings will be OXFF.
So I think this was really a lot, and also a lot of drawings, which are all fun, but let's really try to sum it up once more on a high-level point of view. The personality routine is invoked multiple times during unwinding to decide whether a handler or whether a frame has a handler for the specific exception which was thrown. On the way, it uses the language-specific data area and the exception object as data to basically figure this out. And the action of the personality routine really tells what to do. I mean, besides finding, there's also other things to do. We already saw a couple of times there are multiple phases involved. So the natural question is, what are those phases? So first of all, there's the unwinding phase 1, or also called the search phase. During the search phase, all the unwinder is doing, or the personality is doing, is checking, do we have a valid handler here? And if there's no valid exception handler, it will most likely call unwind resume to go up to the next stack frame to call personality routine on that one. But if there was a handler found, it will return the URC handler found, which in turn initiates unwinding phase 2, which in other words is also called the cleanup phase. And of course, this goes into the action to basically tell the personality routine to do the cleanup things. So during phase 2, the unwinding process is started again from the bottom. And for each stack frame, the call safe registers are restored and the cleanup handlers are called, basically to do stack frame management. In more detail, the cleanup handlers are really, I mean, we saw a little bit earlier in the talk this example where we have the delete operator in it. This is something which would be taken or which would be done by the cleanup routine. So the cleanup handler would be called to delete the object. So in essence, cleanup handlers are there to release the used memory resources and then call unwind resume to go back to the unwinder, which in turn goes back to the personality routine for the stack frame above. Then when we eventually hit, during phase 2, the frame which had the registered handler found, right, where the unwinder found the right one during phase 1, the action which the unwinder gives to the personality routine is UA cleanup phase, bitwise ORed with UA handler frame to tell the unwinder, to tell the personality routine, okay, we need to, we are where the frame is handled, so do whatever you need to do. What is it? What needs to be done? So UA handler frame will basically force the personality routine to try installing the context of the landing pad. So basically to prepare everything that execution can continue at the catch handler. Let's use this for a second to talk again about landing pads. So far we talked about a lot of catch ... so catch all handlers, but in reality you will more likely see code which looks like this. Right, so the catch has some sort of runtime error or like some specific type of exception it wants to catch and then does something with it. What does this tell us? It tells us that the catch handler needs access to this exception object. So how is this done? Here we are back at the installing context operation. So if the personality routine is called with the handler frame and the cleanup phase actions, it will eventually end up in this install context code branch. In here, we have basically a couple of things happening, but most importantly, we have some calls to unwind setgr, so set general purpose register, and a call to unwind set IP, which sets the IP for the context we are operating on. On x86, the first, in general, the first general purpose register which is set is 0, the second is 1. On x86, this corresponds to AIX and RDX, and the IP, much to no surprise, corresponds to AIP. If we go from here and look what these registers are set to, we first start at the very top to see that there is a UE header written into AIX. So this UE header is basically just the exception object. So all good, the catch handler will have access to the exception. On the bottom, when we do unwind set IP, we basically give the landing pad. So this is the address of the handler we want to jump to. So also all good. But then we also see another thing here, the handler switch value. So what is this? For understanding the need for the handler switch value, we need to think a little bit about the differences between language, what we saw in the beginning, and binary, which we saw in the middle of the talk. So in the language part, we have the possibility to have from one try range multiple catch handlers, right, for the different types. On binary base, however, we have basically just this call side table for a single try range, and then a filter to figure out what. So this is the kind of the exact opposite, right? We have only one landing pad, only one location we can go to. So filters are per call side range. The idea to solve it is quite simple. Let's just merge all the catch blocks into a single landing pad. And then, during the landing pad, the first thing which will be done is like checking the handler switch value to figure out what kind of exception we are currently operating on. And this handler switch value is, in fact, also the same value, like the same offset value which is used during filtering to understand which exception we can handle.
So we heard a lot of things. Let's put it all together and recap and figure out what happens when an exception is thrown. So when you see a throw statement like this in a piece of C++ code, what actually happens under the hood is the compiler will emit an allocation for this exception, and it will emit a runtime error initialization for this newly allocated memory. After this, it will call CXA throw, which then in turn invokes, initializes some C++ internal state, and then invokes the unwinder through unwind raise exception. Inside unwind raise exception, we will start by unwinding a single frame, call the personality routine, to figure out whether this frame has an exception handler or any cleanup handlers that need to be run. If there's no handler, it will return continue unwind, and we'll go back and unwind another frame and rinse and repeat. If, however, it does find a handler, it will return an unwind found handler, and we will restart unwinding from the beginning. This time using unwind cleanup phase as an action. The second time we go unwinding, we will again return unwind, continue unwind, but in this time we will call any cleanup handlers that need to be called at this point. If, however, we're in the frame that earlier the personality routine reminded us that there is a handler from it, we will call it using handler frame as a flag set, and it will return handler set after setting up the state using the general purpose registers for the exception, the switch case value, and setting the instruction pointer in the context structure that are used by the unwinder. At this point, the unwinder will transfer control flow to the landing pad, and in the landing pad, we will start by calling CXA begin catch in C++, which does some bookkeeping, have the user code, and then CXA end catch, which again does some bookkeeping and cleanup. After that, we will jump back into the function or return, depending on whether this what this catch handler is at the end of the function. In C++, you can also rethrow exceptions. In that case, we will have a CXA rethrow in the landing pad, and that will call unwind resume, which will go back into the unwinder and continue unwinding. This is incidentally also called by cleanup functions. So this basically means that execution will not continue at this point, but instead we will go back unwinding and install maybe a catch handler further up or terminate. So
yeah, now we are talking, I don't know, half an hour or maybe a bit more already here at Recon, and we still haven't seen a single bit of disassembly. So let's fix that. Let's fix that, right? Time for a live demo. So we basically want to show you a little bit how those exceptions, like all the different structures we just talked about, look like in binary level. And we note that Ghidra and IDA by default have all of those things in the backend as black magic implemented so that they can show you where actually catch handlers are located. Binary Ninja, on the other hand, did not have it yet. So we are here to fix this, and we wrote a Binary Ninja plugin, which we will be releasing shortly after the talk. So meet our new plugin, Binja Exceptions.
So I'll give you a short live demo of that. and we'll start out by looking at some source code.
Damn, no disassembly again.
Yeah,
But,
I mean, we're doing reverse engineering, but maybe it's nice to see what we're going to be looking at first.
forward engineering for a change.
Yeah. So we have a main function that has a try block and 2 catch handlers. This function calls another function, which in turn calls one that throws a runtime error. So pretty simple binary, should be fairly straightforward to reverse engineer. So at this point, I've already opened this in Binary Ninja using our plugin, but haven't invoked anything yet. We'll start by looking at, well, where's my mouse? Oh, I think I'll need to finish this first. So we'll start by looking at the EH frame header and EH frame. As you can see, they have some data in them, but we can't really understand what yet. So at this point, we'll run our plugin, and that will define some information that we can look at. In the frame header, as we explained earlier, we have the initial locations and the addresses of all of the frame description entries. And if we scroll down a bit, we'll find the frame description entries for each frame and the corresponding common information entries. In this case, the function that was doing exception handling was main, so let's find its frame description entry. That's here. Incidentally, the bytes that you see down here, which aren't decoded, are the DWARF information for each of these frames, and this defines how the unwinding would specifically work. The frame description entry for main has an LSDA offset, and in here we see the begin and the range. That basically would help us figure out where these functions are. In this LSDA, let's take a look at that. We have some call site ranges, and this one has a start and an end which corresponds to a try block and a corresponding landing pad offset. These are all offsets from the beginning of the function. There's an action which points into the actions table. So scrolling down a bit, here we can see the actions. We have 2 actions. We start out with action 3. This was our entry point into the actions table. That has a filter of OX1. And then the next one goes on here, which has a filter of OX2. These 2 reference types in the types table. And as you might remember, these types are just offsets to the runtime type information for the exception. So if we go to OXD1D88, as relative to where we are, we'll find the type info for logic error and for runtime error. So as you can see, that's basically the structure of the information in the binary, but we don't just display that, we also parse it to figure out where the handlers are. So looking at those, we'll find there are some landing pads that we annotate, and if we go to main, need to take the tick for relative out. We go to main. Main calls bar, and we don't see any of the try-catch handling at first. However, down here, we can see that there's an exception handler for the function main. And looking at that in disassembly, we have some comments about what range of addresses this exception handler is valid for, what types it handles, and in here we can see that RDX, which, as you might remember, is the second general purpose register. It holds
the handler switch value.
It has, yeah, exactly. It holds the handler switch value, gets checked for 1 and for 2. If we change unwind resume here to be no return, it looks a bit nicer. And we can see that in the case of OX1, we're handling a runtime error, and in the case of OX2, we're handling the logic error. So
in all other cases, we will just unwind resume because somehow we ended up here with an exception we cannot handle.
Exactly. So this way we can find exception handlers. If we look at other functions, for example, this one, these are cleanup handlers. These just perform some generic cleanup, and as you can see, in the end they terminate by calling unwind resume and going further up the stack. So yeah, that's a short intro to what you can figure out using this information that is present in binaries. And with that, we'll go back
to the talk. So far we saw like a lot of internals on how the exception handling works on G++ or GNU-C, on Linux and so on. But what is actually about other platforms? How does exception handling work there? And we won't go into full detail here, but just maybe give a small highlight about which things are different, the key points. So Apple does things differently.
Yep. Apple doesn't use the except frame header table. It instead has a section called unwind info in its binaries, in Mach-O binaries. This one has just a long list of function offsets, and it's basically a two-level page table. The function offsets are corresponding to ranges. The second level pages then go onto another table which has for each function a function offset and an encoding. This encoding says how to unwind a specific frame. This encoding in its top byte encodes a few flags. For example, whether this is a function start or not, whether it has an LSDA, and a 2-bit index into a global personality list. So you can have up to 4 different personality routines. The next 4 bits are an opcode. For example, for x86, this encodes whether it's an RBP-based stack unwinding, so we'll use the frame pointer, whether it's a constant that we're subtracting from the stack frame, whether we're using a value in a register, or whether we're using DWARF information. The next 3 bytes of each entry are some operands which are dependent. For example, in the case of DWARF, this will be an offset to the corresponding frame description containing DWARF information. So each of these frames is 8 bytes big, and that's pretty big if you have a lot of binary with a lot of functions, and a lot of this might be compressible. So there's a second type of page table, which is the compressed second level page table, which has 4 byte entries, so you can fit double as many things in there. And each of these is in its lower 3 bytes has an offset of the function, and its high byte has an index into a table of encodings or a global table. So you can have somewhat smaller unwind information that way. So, and then there's the LSDA index array. So this is fairly straightforward. For each function, it just encodes where the LSDA is. So, bit different, but still fairly straightforward. Windows, on the other hand, has structured exception handling, and we will just very briefly brush on this. Structured exception handling contains all of its exception handling metadata on the stack. And it's a linked list where each frame has a list of handlers that are implemented. And there's a lot of write-ups online about how structured exception handling works and also how to exploit it. So if you're interested in that, there's already a lot of prior work that you can look at there.
And that kind of concludes more or less our talk. So let's do a small recon recap. So we started looking into the language semantics of C++ exception handling. How does it look like on the language level? We continued looking into how unwinding works. From there, we had our small little fun side quest to DWARF. Continued looking into the personality routine, the language-specific data area, and lastly, we looked into landing pads and handlers. And this is basically how we try to demystify the mysterious life of an exception. We hope it was nice for you, and if you have any questions, we are here right now, or you can send us an email later on. Thank you.
Thanks for the talk, guys. So I had a question regarding the cleanup routine. You said the cleanups are run before the exceptions are handled. So how is it decided what counts as cleanup? Like the delete instruction, for example, could be inside another function, right? Like you call a function which does a delete on that pointer. I mean, how is that figured out?
So basically, the cleanup handlers are there. So if I understood the question correctly, it is about how the unwinder would know when to call the cleanup handler, what needs to be destructed from the stack, and so on.
Yeah, or what part of the remaining code after the exception counts as cleanup and what doesn't count as cleanup?
In reality, like part of the code is doubled. It's once in the like normal execution of the handler of the function, and then at a different location at the cleanup handler, where during unwinding we can jump to. So the compiler will figure out what needs to be deleted or what needs to be cleaned up during exception handling, and embeds this in the specific cleanup handlers.
Right, and those deletions don't have to be explicitly defined. Those can be just normal destructive.
Yeah, exactly. Just if I mean, I think so. Right?
It's basically if your variable has automatic storage and it's cleaned up when the frame is being removed. So when you're returning or through exceptions, anything that has automatic storage will be freed.
Got it.
So if it has destructors and it's a variable with automatic storage, then there will be some cleanup handler emitted to call that.
Yeah, thank you.
Yeah, so you guys described that this whole process is kind of spread out over multiple descriptions, entities. Could you guys briefly describe like which pieces you had to consult and like who's responsible for which pieces?
Yes. Absolutely, we can do this. So basically, the throw itself, like issuing the throw, is done by the binary, which is CXA throw. CXA throw will call into libstdc++, which then in turn starts invoking the unwinder, which is on itself located in libgcc. Then this will do a bunch interaction back with libgcc++, to then eventually, when cleanup handlers are found and so on, jump back into the binary.
Okay.
Yeah.
And this is all like specific for each of the libraries. You guys had to
Yeah. So the common part is basically part of libunwind. Libunwind is the unwinder. The standard that it implements is the Itanium CXX API, which is used it's used on Itanium and for C++, but it's also used on all other platforms, and it's used by a lot of other languages apart from C++. So the unwinder doesn't know about types of exceptions, it only knows how to unwind, and it will invoke the personality routine. The personality routine is specific to the language runtime. So for example, in the case of C++, unwind resume, unwind raise exception, and so on. These are all part of the libunwind. CXA throw, which calls unwind, throw, raise exception, or the personality routine and so on, are part of libstdc++, which is the language runtime. It's language specific. So for other language runtimes, for example, Objective-C, the personality routine and the specific throws, semantics, and so on will be specific to that language in its language runtime. However, it'll use an unwinder. There's multiple different implementations of unwinders. GCC has one. There's also a Clang lib unwind. There's non-GNU lib unwind. Yeah, there's multiple implementations. These are usually part of your C runtime.
Thank you.
Great presentation. Did you look into, I know you said that you're not going to talk about the processor stuff and all those exceptions, but did you look into the libc or anywhere that which routine is the one which gets called when, let's say, a null pointer exception happens, because OS has to transfer control to that eventually?
I'm sorry, could you repeat your question? I didn't catch that.
So my question is, like in your try block, you are explicitly throwing an exception.
Yes.
But let's say you had a null pointer dereference there. Then also you will go into the catch block. What happens?
No, null pointer dereferences are caught by the CPU, that's a different kind of exception. This is not a language level exception. That would be the operating system would, the CPU would trap and the operating system would handle that. On Windows, that's very similar to how exceptions are handled in a program. On Unix-like languages, for example, what we were looking at here on Linux, ELF binaries, or on macOS, those are handled by the CPU and are handled by signals, as far as I understand. So a signal would be sent to your binary, and you would need to have a signal handler. That's not done by exception handling per se.
I see. So there wouldn't be any unwind; it will just terminate.
I'm sorry?
So there won't be any unwind if it wants to catch, and it will just terminate the program.
No, in the case of a floating point exception or a null pointer dereference, what would happen is if there's no signal handler involved, the program would be terminated. If there was a signal handler involved, it would be invoked, and it would be up to the program to decide what to do with it.
Okay. By the Windows do have static data. It's in the 64-bit. 32-bit is the one which has the linked list.
I'm sorry, I didn't
I
catch
meant to
that.
say that in your presentation you mentioned that Windows has structured exception handling using a linked list.
Yeah.
That's only true for 32-bit, not for 64-bit. They do have metadata, which is pretty much like what ELF or Apple has.
Yeah, it also does. There's also unwinding on Windows, but we didn't go into detail on that.
Thanks for the talk. It was great. Are you planning on releasing your plugin in the amazing Binary Ninja plugin manager?
Yes, we are. So we have a few minor things to still iron out, and then we'll be releasing it and we'll be pushing it into the plugin manager, so you'll be able to download it and install it from there.
Briefly, could you explain what the differences might be in terms of the exception handling process if you have let's say, a stripped executable that's been stripped of the dwarf information?
You mean as an interpreted language compared to a compiled binary?
So if you compile, like, if I have a C++ program and I compile it and then I run like the strip program against it and remove a lot of the debugging information, I guess the question is, what dwarf information, is some dwarf information still there?
Yes.
And is it like everything would be the same as you just described?
So there's three different things that can happen. Stripping a binary removes the symbols. It doesn't remove the dwarf information. So if you compile a binary with -G and strip it, I think the debug information will still be in there.
Okay.
Unless you specifically tell strip to remove that as well. Then there's two different sections. There's two different places where you can have a dwarf information. You can have dwarf information for structure layouts and variable placings and so on. That's debug information. That's in, I think, the debug frame section.
Okay.
On the other hand, you have another kind of dwarf information in the exception handler frame, and that's always present, even in a stripped binary. So you'll keep that information in stripped binaries, and that'll also still help you, for example, find out function entries and so on.
Okay,
And
thank you.
Yeah.
So what would happen on allocator failure when it allocates the exception object?
Sorry?
What if the allocator fails when it's trying to allocate the exception object?
If the allocation fails during throwing of an exception object?
Yes, like
I think you'd be in very interesting, I'm not sure if defined behavior land. So yeah, I think the answer to that is I don't know. Probably interesting things.
Okay.
Any other questions still? All right.
Done.
Thank you so much.
Yep, thank you.